question about what defining sustainability. I was appointed to my town's sustainability committee, and the first action that we took was to decide not to define sustainability. Because we were appointed for 2-year terms, and we figured it would probably take us 2 years to agree on that definition. So, but in all of our minds, there may be a slightly different definition, but in my mind, it captures a lot of thinking broadly rather than narrowly, so that whatever solution you come up with is one that can be sustained in the face of all kinds of different pressures. So, in other words, not just a narrow slice. We define something very narrowly and come up with this answer to that particular part of the question, and then later we find out that uses too much energy, or that costs too much, or that can't be sustained by the community. Instead, you consider the whole range of factors at the start to come up with a durable solution. So that's roughly what it means in my mind, but I think we could easily spend the whole day as a group, and we'd all learn a lot from trying to define it. But as long as everybody has somewhat of a rough idea, so that's my working definition, is something broad that leads, a broad look at a problem that leads you to a more durable solution. Okay, so I guess first thing is I put this picture up there to remind myself and everybody that there's something really important here that we're trying to preserve and restore. And that when we think about the problem that we're facing, we shouldn't think about it as a legal problem or an engineering problem or a regulatory problem. It has aspects of all of those things, but it's really an environmental problem and a community problem. And so what we need to keep in mind, and this is part of taking this broad view, is that we're out here to do something that to save something that we value. And all the other things, the laws and the engineering options and so on, are the tools to get there. They are not the ends in themselves. So that's why I put this picture up there. The other thing I want to point out at the start is that speakers don't always choose their own titles for their presentations. So my assigned title is Multiple Benefit Infrastructure, TMDLs and Modeling, which is maybe the least catchy title I've ever given. So in trying to decipher what that meant so I could figure out what to talk about, what it really means to me is taking this broad view, multiple benefit rather than single benefit. It means looking at a whole range of things and coming up with a solution that really serves the whole, what Valerie was talking about, the whole range of benefits that we need to get to, not just isolating a single thing. So that's what I'm really going to talk about. And I took the liberty of changing it in my slide thinking first. Okay, so I'm going to give an example of what we don't want to do and what we have often done in the history of how we've implemented this expensive unfunded mandate, as it was referred to somewhat accurately. So there's one person in the room who's going to recognize this chart. Do you recognize it? This is from an actual environmental project. This is from the cleanup of Boston Harbor, and it was actually reproduced in an EPA guidance as an example of how to analyze things. This, what you're looking at is all of the different points on that chart are different technology options for addressing sewer overflows into Boston Harbor. This was produced in the early 90s. So it's somewhat dated, and this is but it's a good illustration of an approach that we're very familiar with and comfortable taking. What you see is along the bottom is how much of the bacteria load we're reducing by each option, and what you see along the y-axis is how much it costs. And so this is basically illustrating a curve. You spend more money, you get more removal, and so it gives you some sense of cost versus benefit on how much pollution you're controlling versus how much you spend. And so you can look at those options, you can plot a curve through them, and you can either calculate this mathematically, and then you can try to figure out where on this curve you should be. And what engineers like to do is look for the knee of the curve. That's the point where the marginal benefits start to be reduced, the marginal costs start to exceed the marginal benefits. So often will be driven to look at solutions near the knee of the curve, so these two options. Sometimes EPA will try to push higher on the curve. We'll say, well, you spend a little more money, 80% is a lot better than 60%, so let's push up here even though it's higher on the curve. Doing this kind of analysis might tell you it's crazy to do this. You can get more benefits for things that cost less, so you rule that out. The most you can possibly get is this. So this is the kind of analysis we're used to doing, a single pollutant versus the cost, and pick the point on the curve. And that's actually what we did. I can't remember which point we picked. It was probably this one. Do you remember?
It was right at the knee of the curve.
Oh, I lost them. So this is an illustration of taking a narrow view, and there are reasons why we tend to take narrow views. This is an analysis that's pretty well bounded. It's easy, relatively easy to do. There's technical complexity. I don't mean to minimize the engineering work behind it, but in terms of analyzing the issue and in terms of decision makers being able to understand the question and come to a decision point, this is a pretty simple way to look at a problem. And so it's understandable in that light why decision makers would ask for this kind of analysis and why decisions would be made based on this kind of very simple one parameter thinking. But what if you cared about other things too? For example, what if you were interested in how much energy would be consumed by each of these options? Maybe 2 or 3 of them involve pumping. And so you're going to have decades of energy costs, and maybe some of them don't involve any pumping. Maybe some of them have neighborhood impacts that we might be concerned about. Does one involve ripping up all the streets and maybe another one doesn't? Are there other environmental issues like impacts on wetlands, or there could be a whole range of issues. There could be air pollution issues. What if we need a generator to run pumps, but it's in a residential neighborhood? So are there air issues we should be concerned about? None of that's captured on this chart. So what we really need, if we're going to think about sustainable solutions that address a multitude of benefits, is a way of analyzing that takes into account more than 2 things, more than just cost and a single pollutant. It needs to take into account the whole range of things that we're interested in. So one big step towards sustainable green solutions is for decision makers to come to that realization that we need to take a broad look. But that's not nearly enough. That's a big step. It's a step that's only begun and is in progress, and we're not nearly there yet, but it's a step that many people are starting to make. But that only gets you maybe, I don't know, 10% of the way there, 20% of the way there, because then what do you do once you realize it's important to take a broad view? We have tools to take narrow views. We have really well-developed tools. We know how to do this. What are the tools to help us actually take into account a broad range of considerations, to define what they are? What do we want to look at? How do we analyze it? If you want to present information to a decision maker and you're looking at 20 factors and not just 2, how would you put it on a piece of paper? So there's all kinds of questions. We need tools in order to do this. So one of the ways EPA is trying to facilitate this shift towards a more broad and sustainable view is to actually develop some tools that could be not quite as simple as this, but simple enough that they can actually be used and help make decisions. So what I'm going to do with most of my time is to give you an example from a neighboring watershed, the Narragansett Bay watershed, where we're developing a tool as a pilot to try and take this broader view. All right, I was done. All right. Okay, so here's an example of complexity. If you're going to look at more than 1 or 2 things, this is a greatly simplified diagram of some of the things that we're trying to capture when we're looking at Narragansett Bay. And I didn't mean that in jest. This is greatly simplified from what is actually in the model that we're building. We're trying to find a way to capture all the things that need to be captured to make a good decision, but at the same time, boil it down enough so that it's actually useful to people who need to understand it and make the decisions. So clearly there are many factors here, and the point, and I'm not going to go into detail because the point is not to explain all the boxes here, but just to illustrate there are a lot of different things that we're interested in. There's a big nitrogen problem in Narragansett Bay, so nitrogen is up here, but it's one of many, many things that we're concerned about. So one thing is there are a lot of factors. Another is there are a lot of relationships between factors, and if we're going to be able to make decisions and not just be overwhelmed by complexity, we need to be able to define what these relationships are and start to model them. So you can see lots of arrows, and it's a simplified version, so there are other arrows that should be on there, but they're not because they're not as important, but they're in the model, just as there are other factors in the model that also aren't up here. So for example, if you improve wastewater treatment, that this box right here, note that's only one of the options that's available for evaluation in this model. If you improve wastewater treatment, you can reduce nitrogen loading, so there's a relationship there. One thing that this model allows us to do is to identify where there are loops, because one of the things that happens when you look at lots of things all at once is there are relationships that wind around and form a loop. So, for example, if we improve treatment, we also increase energy use. If we increase energy use, we'll increase emissions to the air and the deposition of pollutants from the air. Some of those pollutants are nitrogen. They'll run off into stormwater and come back and increase nitrogen loading. So here you have a pretty complex interaction between if you improve treatment at existing treatment plants, you might lower loadings here, but then increase them through this loop. So conceptually, we can all understand that. How important is each of those loops? We can easily quantify how much nitrogen will be reduced by improved treatment. What's the relative impact of increasing emissions by increased energy use? Is that trivial or is it important? And so there are all kinds of loops like that in the model. We can't, in our head, get a feel for that. We have to be able to start quantifying. There may be 20 loops like this that all interact with each other. So that's where you need computational models to start weighing it all against each other.